So for display, you have to prepare the spectrum, and typically the magnitude is taken, but the magnitude could be sometimes 0. And when you take the log after that, so that the difference between very high values at DC and very small values at high frequency components can be compressed, then to the magnitude you add 1 to avoid taking log of 0. So log base 10, 1 plus magnitude square, log magnitude square is what is typically displayed, and also it is common to fold or shift the spectrum so that the DC or 0 frequency is in the middle. And you show the full spectrum, not half. There is an interesting way to do that by multiplying alternating pixel values with plus and minus 1, which is explained there, but I'll skip that for now. When you rotate an image, these are the rotation coordinates by angle theta, then the frequency domain Fourier transform is also rotated in the same manner by this transformation. So that we saw with the rectangle image, and that helps in analysis of directional or oriented patterns. We will see some applications much later. Scaling an image leads to inverse scaling in the Fourier domain. FAMBN is 1 over AB, FK over AL over B. So if you multiply by A here, the corresponding frequency component is divided. So if you go faster in the time domain, high frequency is increased. If you go slower, low frequency is increased. So there's an inverse effect. The shrinking of an image leads to expansion of its spectrum with increased high frequency component. I showed that with the Fourier transform of the rectangle image earlier. Linear shift invariant systems, I already mentioned this. We have convolution in the space domain when a signal or image F is passed through a linear shift invariant system with impulse response HMN. And the output G is the convolution in 2D. So if you remember 1D convolution, it would have been H alpha times Fm minus alpha, or HT F of, or you use some other variable H alpha F T minus alpha, D alpha. Now we have two variables, and instead of integration, we have summation. There'll be more examples, numerical examples coming later in filtering. So when you take the Fourier transform, multiplication becomes convolution becomes multiplication. And of course, the converse, multiplication becomes convolution too. So both ways. So if there is convolution in one domain, in the other domain you have multiplication. So the convolution multiplication property with the DFT implies periodic or circular convolution, which is an important point to remember when filtering. When you filter in the space domain, you apply a mask and filter, and there is no issue. But when you do convolution in the space domain and you want to look at the corresponding effect in the frequency domain, then we have to remember that there is a distinction between periodic and circular convolution versus linear convolution, which is what we are seeing. And I'll show you some examples later. Multiplication of images leads to convolution of their Fourier spectra. Convolution leads to multiplication. Multiplication leads to convolution in the other domain. In time domain signals, it is not common to encounter multiplication. You encounter addition of signals and convolution. But in images, it is possible. What you're seeing here is a multiplication of an illumination pattern of the lamp there. It is transmitted through some sort of, let's call it transparency with these letters, and that is projected. So if I put this, then that is multiplied with the transmittivity of this, which is 0, so you get my shadow. So the image you see, or record, is a product of the illumination function, the light field, with the reflectivity, if I take a picture using a camera, reflectivity of your, whatever the pattern here is, or transmittivity if I'm sending it through film or some transparency. So GXY is FXY times SXY. S is the light source intensity field. Normally we assume SXY, the light, to be uniform, in which case there is no problem. But typically around the edges, around the periphery, there could be some reduction in light intensity, or there could be some other modulation. If that happens, then your image is distorted. Sometimes it is used for advantage by projecting some other pattern to analyze the contours of the body and so on. So there are some benefits to purposefully introducing modulation and multiplying the image with some other pattern, a known pattern. But in some cases, this pattern may be unknown, and that causes non-uniform illumination, and you may want to correct for that, especially in imaging of the retina using cameras, fundus cameras. If SXY is absolutely uniform, its Fourier transform is a delta function. Constant field, Fourier transform is delta, with some value A. And convolution with delta doesn't matter. It doesn't have any effect. So convolution of FUV, the A delta, will have no effect. Otherwise, GUV, the Fourier transform of the image that you have acquired, is the convolution of the Fourier transform of the original unknown image with the source illumination function in the frequency domain. That convolution mixes up the frequency components. And if you want to correct for that, you have to do deconvolution. And for that, there are homomorphic filtering techniques, which I'll show later on. So all of these properties of the Fourier transform have important implications in practical applications. And I'll show them later. First the theory and then some applications or examples. The correlation of two images is expressed in terms of FMN times G m plus alpha n plus beta. Now the shift is given as plus. And the integration or summation is on m. So there is no reversal. Convolution, you have to reverse one of the signals. But here there is no reversal. So you have one image, you have another, put them together and shift and multiply, integrate for every position. So that tells you what is common between the two. You can do template matching. If I'm searching for some pattern, I take a picture of that pattern and multiply every position where I want to search for that. Where I get a match, that output will be large. You can compare images, two images of the same person or some other picture that you want to compare. What is common between the two? Is there anything common? Maybe there is a target and it's displaced here. So you want to find that. When you take the Fourier transform, you get the Fourier transform of the two images multiplied, but with one conjugated. Similar to convolution, but because there is no reversal, one of them will be conjugated. If you want to normalize the correlation coefficient, then you multiply the two images, integrate, and normalize by the geometric mean of their energy values. There is no shift here. If you want, you can put a shift, m plus alpha, n plus beta, and do it for every shift. Otherwise, if they're registered, the images are registered, you just want to compare for any changes without shifting. Just multiply the two images. It's like take the dot product. It's a dot product of projection of one image onto another, summed over all m and n. This is the energy of F. This is the energy of G. Multiply and square root. That is the geometric mean of the energies of the two functions. Now gamma will be between 0 and 1, or plus and minus 1, depending upon how the changes have been made. Differentiation of an image leads to high-pass filtering. If you take the partial derivative of fxy with respect to x, you get j2 pi u fuv. Some of these you can prove easily. Take the Fourier transform definition, apply the derivative. You will get this j2 pi u out from the exponential. We have done that in 1D. The same is happening in each dimension now. If you do in the y direction, you get j2 pi v. So what is it doing? It is giving you the spectrum of the original image multiplied by this j2 pi v. Take the magnitude, just v, forget the 2 pi. It's increasing linearly. So the gain of this filter is increasing linearly with frequency. So high frequency details get more gain. Low frequency components get lower gain. DC gets zero gain, so DC is removed. So you lose the intensity, the average intensity is lost. Brightness is lost when you take the derivative. Higher frequency components are related to edges, so edges are emphasized. But there could be noise present at higher frequencies, so noise will also be increased by this operation. It is useful in edge detection, as you will see later. With digital images, you just take the difference. Derivatives are approximated by first order differences, fmn minus fm minus 1n. Now, is this horizontal or vertical? It depends upon the array notation or matrix notation, which one you use. So this is where I said one needs to be careful in the interpretation and implementation using array notation or matrix notation. The directions will change, horizontal or vertical. So if it is y or x, it depends upon which way, matrix or array. And sometimes it doesn't matter, but in some cases it will matter. And the other derivative, fmn minus fmn minus 1. The previous pixel along the horizontal or vertical direction. When you take differences, there could be negative values. So the question is, you want to display the result, how do you display negative values? You may take absolute, but then you won't be able to differentiate between an increase of this step or a decrease of that step. Both will come out the same way. So you may want to shift the whole thing. Find the minimum, maximum, and transform linearly to 0 to 255. So there will be an average gray level for 0. Negative values will be dark, positive values will be bright. I'll show some examples. So you need to map the full range of the pixel values, including negative values, to the display range available, typically 0 to 255 using 8-bit display. Magnitude may be displayed if the sign of the result is not important, but typically it will be important. Differentiation results in the removal of the intensity information. The brightness is lost. The values of the spectrum for u equal to 0 or v equal to 0 will be 0 in the result. Like this. The rectangle, that's what we had. Differentiation this way, you have that, negative and positive there. And this is the Fourier transform. And differentiation that way, you get this, and this is the Fourier transform. Lines, this is a sinc function, but of two lines. This is also a sinc function. At DC, it is 0. Brightness is gone. If you take the integral of this, it will be 0. Not in the display, but the actual pixel values. Okay? So the myocyte image I showed earlier, I rescaled it, Fourier transform, differentiation, horizontal, vertical. You see some edges here. Here, these edges are emphasized. There, some vertical edges are emphasized. Depends upon the orientation. This is an MR image of the knee. It doesn't matter. In this example, it's just a picture. So when you take the derivatives, you get the edges. And the Fourier transform shows some oriented components because these are like lines at different angles. Note that this is 0 here, and it is 0 there. So taking derivatives is useful in the detection of edges and rapid changes. Small changes will give you small values. You may not care about that, but large changes will relate to large differences or strong edges. When you combine the derivatives and take the second order derivatives, you get the Laplacian. The Laplacian is the partial derivative of second order in x and y added together. And in the Fourier transform, the first derivative gives you j2 pi, second derivative gives you j2 pi square. So you get j square becomes minus 2 pi square u square plus v square. So now you have gain in the frequency domain applied to the original Fourier transform quadratically increasing in u and v. So higher frequencies are boosted even more than with the first derivative. And you get stronger output for edges in the image, but also noise will be emphasized even more if there is noise. This is isotropic, meaning it is not sensitive to direction. So we also call it an omnidirectional operator. It is sensitive to edges in all directions, whereas the other gave only vertical or horizontal edges. You implement in this manner, the second derivative is fmn minus fm minus 1 minus the derivative at the other place, fm minus 1n minus fm minus 2n. That turns out to be fmn minus 2fm minus 1n plus fm minus 2n. So it's a 3-point difference. But in image processing, causality is not important. In 1D signal processing, your operations have to be causal. You cannot look ahead in time. But in images, you can, what is ahead and behind? We'll say, okay, if I look this way, it is ahead, that way is behind, and top and bottom. If you're scanning using raster scanning, there is some order of scanning. But otherwise, if you're given the whole image, up, down, left, right, doesn't matter. So you can rearrange this and shift by 1. So applying one shift, you get the result as fm minus 1n minus 2fmn plus fm plus 1n. So weight of negative 2 for the center pixel, plus 1 for the next and next. The same top and bottom. So those are the second order derivatives or the Laplacian. I'm sorry, this is the second order derivative in x and y. You combine them, the Laplacian, you add them, you get this mask minus 4 times for the center pixel in a 3 by 3 mask, plus 1, plus 1, plus 1, plus 1, top, bottom, left and right. The corner pixels are not used. So this is the filter representation called a mask or a 3 by 3 filter operator, also the point spread function of the Laplacian operator. Apply it as a convolution. Shift and multiply and integrate over this. So it's a differentiation operation, second order. But when you add all these coefficients, it is 0. So the brightness is removed. There is no average value of the the average value is 0. So this is known as the Laplacian. So it detects edges in all directions for that rectangle image. But you see there are double edges, positive and negative, when you cross an edge. So you get a double-edged output, which you may or may not like. Positive and negative. If you take the absolute, positive, but it's thicker. The myocyte image, the knee image, some images, some edges. So you see all the edges here in all directions. So the opposite of differentiation is integration. And it should be having the opposite effect. If one is high pass, the other is low pass. Integration is filtering, integration, accumulation, so smoothing. So when you integrate alpha minus infinity to xf alpha y, you're integrating in the x direction only, you get 1 over j2 pi u as the gain factor in the frequency domain. And 1 over j2 pi v if you integrate in the other direction. So these are now decreasing with frequency. Higher the frequency, the lower this weight. So high frequency components are suppressed. And that is low pass filtering. Now in signal processing, sometimes you may integrate from minus infinity to the current time, usually in theoretical representations. But in practice, there is an origin somewhere and you integrate from there. In image processing, you don't start from somewhere in the image, you integrate over a small area, not from the origin, wherever that is. So you integrate over a small window or aperture. There is no need to integrate over the whole image. If you integrate over the whole image, you get the average value, that's useless. So you integrate to get GXY as 1 over AB, you are integrating over a window of size A by B, half up and down, centered at the current pixel, fx plus alpha, y plus beta. Alpha and beta are the shifts. Integrate d alpha, d beta. So sometimes I use continuous notation because it relates to certain aspects, like the aperture in an imaging system. Here it is square, but typically it will be a circle aperture. So this is also called a moving average filter because you are integrating here and then you are moving as you shift, as you change alpha and beta for different x and y, you are integrating. So as you evaluate this function for different x and y, you are shifting over the entire image. So you are averaging over a small window. So that's why it is called a moving average filter. The average is taken over a small window that is moving. Typically, the aperture is a small 3 by 3 window, 3 pixels by 3 pixels, centered at the current pixel being processed. So it turns out to be, in the discrete notation, 1 over 9, alpha, beta going minus 1 to 1, minus 1, 0, 1. Fm plus alpha, n plus beta. What is that? Fmn in the middle, previous row, m minus 1, previous column, n minus 1. The previous row, 3 pixels. The current row, 3 pixels. The next row, 3 pixels. 3 by 3. The weight for all of them is 1 over 9. So you can write it like this as a mask for convolution. So this is a rectangle function. So in the Fourier domain, it is a sinc function. So your image is, if you convolve the image with this, the Fourier transform is multiplied with this sinc function. The sinc function, the side lobes keep getting smaller and smaller. So it is a low-pass filter, all right, but the gain is not uniformly decaying. It is going up and down and up and down and negative and positive, which is not good. So it's not a good filter. It is commonly used, but it's not a nice low-pass filter in the sense that you want filters to have a continuous response in the frequency domain, smooth. But this is up and down, but we use this often. You can also do this in 1D, horizontally and vertically, by using only 3 pixels, either along a row or a column. If you go along, if you write like this and like that, if you want to write 1, 1, 1, to avoid interruption of the text, you write it as 1, 1, 1 and put a transform. So T is a transform. It's a column vector. So watch for that little T there. It's hard to see the difference, blurred that way and blurred this way. But in the frequency domain, you can see these components are reduced. Those components are reduced. This is in 3 dimension, in all dimensions, 3 by 3. So this much is retained. And all of those high frequency components have been reduced. The myocyte picture again, I think it's enough. 2 pictures will be enough. This is applying the filter in both directions. I'll skip that. They don't need so many pictures. In the book, I put so many pictures, but not necessary. That's the basic idea. Modulation transfer function is a Fourier transform of the point spread function, as I mentioned earlier. Some authors call it modulating transfer function. In electrical engineering, we call it frequency response. MTF is commonly used in image processing, modulation transfer function. In optics, it is called the optical transfer function, also OTF, in some references. So the Fourier transform of the original image that you're trying to capture is multiplied by the modulation transfer function of your system. And what you get is GUV. You don't get FUV. There's always some distortion. So these are the Fourier transforms of the original image or the scene that you want to capture. G is the image that you got, and H is the point spread function. There are some books, as I said, they call this as the optical transfer function, and its magnitude is called the modulation transfer function. So you have to be a little careful when you switch from engineering books to physics books. There could be some change in terminology. If you want to be more specific, you should say magnitude transfer function if you take the magnitude. But there is some variation in the literature. So the width of the point spread function and the corresponding modulation transfer function are important. In the image domain, if the point spread function is broader and broader and broader, there's more and more blurring. But if the point spread becomes bigger and bigger, broader and broader, the MTF becomes narrower and narrower, more and more low pass. So the width of the point spread function and the MTF have an inverse relationship. The greater the blur, the wider the PSF, and the narrower the MTF, more low pass. More high frequency components are attenuated significantly. Resolution, I mentioned a few definitions of resolution. You can also define that in the frequency domain. Some of us, especially in electrical engineering, we like to work in the frequency domain. It is a point along the frequency axis beyond which the attenuation is substantial, significant. How do you define significant, substantial? You have to set some rule, 10% of the maximum something, and say, that is my resolution. Beyond that, it's too much of loss of frequency components. They're being suppressed too much. You can also take the area under the MTF. If the MTF is big and broad and going to high frequencies with substantial values, there's more area under the curve. If it is flat, it means there is no loss. More area. And if it is narrow, very, very blurry, low-pass system, the area under the curve is very small on the whole axis. So area under the MTF is another measure of the resolution indirectly. Larger the area, the better the system, because it is passing more frequencies with good gain. More high frequency components are preserved than a system with a small area under the MTF. So here's a practical application of that. I got this from a paper here, and I have compared the MTFs of a digital radiography system. These are old, but the illustration is important and very illustrative in the sense you are comparing the MTFs of a few imaging systems, whatever they are, it doesn't matter. One is a DR, digital radiography system, with an image intensifier television. In those days, they were using a TV camera and then digitizing the TV signal to get a digital image of a radiographic image mounted on a light box. Old technology, and then screen film system, X-ray with X-ray imaging with film plus screen. And FS is focal spot. I mentioned earlier, if the focal spot in the X-ray tube is too large, there is blurring. So they are comparing here. This is image intensifier TV with 0.8 millimeter focal spot and with 0.3 millimeter focal spot, and this is screen film. Obviously, screen film was at that time better than the digital. More area under the curve. This is normalized 1 up to 5 cycles per millimeter. Here, the two of these digital systems are fairly close. There is not much of a difference, but there is a small difference. The larger the focal spot, the more the low pass. The area is reduced a bit. Okay? So all of these, as I said, are important in practice. There is another type of representation of image quality in terms of contrast detail. It's based upon experiments with images of objects, square or circle or something. The threshold object thickness is determined as that related to the lowest contrast image where a radiologist or whosoever is using the image could visually detect the objects with a 50% confidence level. So you make a phantom, a test image, typically they use foils of gold, could be aluminum or some metal, different thickness and little pieces, squares or whatever you want, and different thickness and different size. If you just want contrast, just the thickness is varied. The thicker the material, the more the attenuation of the X-rays. And if it is very thick, there is more attenuation, so contrast is reduced. If it is very thin, X-rays pass through, you get higher contrast. So as this arrangement is done and you go through that, you ask the viewer, can you see all of these? Or where is it that you cannot see the objects anymore? And you say, okay, that's my resolution. But you cannot just do it once, so you say do it many times. And then you calculate 50%. 50% of the time, the viewer should be able to detect that object. Then it is passed, otherwise it is not. So you find the cutoff point where the observer cannot see the object anymore. That is the contrast at which detection fails. And you can plot that. Object size, millimeters, threshold object detection thickness in millimeters. And then for different imaging systems, the image intensifier TV digital radiography system, screen film system. They plotted these curves. So for a given object size, with the screen film, you can detect thinner objects. With the digital system, the object has to be thicker in order to be detected. MTF curves here for screen film, an amorphous selenium detector, and indirect digital mammography. Digital imaging system, but indirect meaning there is an analog system that is scanned. So this was from a company called LORAD. So the indirect digital system is poor compared to screen film, the original analog mammograms that were the standard at that time. The amorphous selenium system is better. Again, you have to look at the area under the curve. Up to 10 cycles per millimeter. So about 0.1 millimeter resolution. So this is how you compare imaging systems using these parameters, modulation transfer function, which is related to point spread and so on. There's an example I'll show you of the MTF of a microcomputer tomography system for high resolution imaging of small lab animals. Nowadays, there are microcomputer tomography systems with a small bore where you can put your hand or put your leg, and you can get high resolution CT images with resolution. At that time, it was 55 line pairs per millimeter. Nowadays, it's perhaps more than that. Much better, maybe 100 line pairs per millimeter. But you can't put a whole human body into that, just for the wrist or the fingers and so on, to diagnose arthritis and such issues. The spatial resolution was found to be about 9 micrometers for this system, where this is a French team. This is old, 1996, but this illustrates what I talked earlier about with the edge spread function, line spread function, and so on. They first got the edge spread function. Taking an image of an edge, it's certainly not a step function. There is some blurring. They take the derivative. This is the line spread function. From that, they derive the MTF. Isotropic, so they are showing only this one section for positive frequencies, up to about 80 line per millimeter, it is 0, it's gone. So they did some measurements and said up to 55, it is good. Gain of 0.1 compared to the maximum. So they said that's the limiting resolution, 9 micrometers at that time. So now it'll be much better with new systems. But I like this illustration that all these things we talked about can be put to real use. When there is noise, typically we assume noise to be additive. In 1D signal processing, mostly it is additive. In image processing, sometimes it could be additive, and most of the time additive, sometimes multiplicative also. But let's start with additive. GXY, the image you get, is FXY, the original image, plus eta XY, some noise field. So we are assuming it to be additive and also statistically independent or uncorrelated with the image. That's an assumption made. If you take the mean, mu G is mu F plus mu eta. But mu eta typically is 0. Random noise will have 0 mean if it has positive and negative values. There are some types of noise, like Poisson noise, which only has positive values. Then that doesn't work. So if your noise is having 0 mean, then the mean is preserved. The variance is sigma square G is sigma square F plus sigma square eta. So the sigma square is a measure of the energy, the variability in energy. So that's the mean squared value. So the mean squared values get added up of the noise and the original image. Signal to noise ratio, there are a few different definitions that are commonly used. One takes the ratio of the variances of the original signal and the noise. How do you get the noise? How do you get the original variance? You need to estimate that. And 10 log 10 of it is already squared. If it is not squared, you take 20 log 10. So variance of noise is estimated by computing the sample variance of pixels from background areas or with your camera shutter closed or your cap closed. But the CCD detectors will have some noise. You measure that. No input, no light input. That's an estimate of the noise. Or you may have an image where that's the image and there's nothing here. So you take a few pixels from here, take the variance. That's noise. Nothing is supposed to be here. Variance may also be computed from the PDF or the histogram if you have it. The variance may not always be useful. Sometimes what is more useful is the dynamic range. Variance of the image in particular is not always useful, but you want to know what is the range. So another measure of SNR that is commonly used is F max minus F min, the dynamic range, normalized by not the variance but the standard deviation, just to maintain the dimension, and 20 log 10 because they're not squared. Typically, in the days we were doing our research, this was expected to be of the order of 60 to 70 dB. 40 dB, most researchers were happy. But 60, 70 dB was considered to be very good signal to noise ratio in image display systems. Again, nowadays that's much better. These numbers may not be relevant at this time. What is also important in display is what is the frame repetition rate in your display so you get a steady image, and is it interlaced or not? Are you displaying all the data or are you displaying only alternate lines like in old TV? But perhaps you would not encounter interlaced display now. They will all be non-interlaced perhaps. Contrast to noise ratio is another measure where you see something similar to background, foreground minus background divided by background. But now it is a mean of the foreground minus mean of the background, like what we had F minus B earlier, but the denominator is sigma B. Sigma is standard deviation of the background. And that could be computed in a background around the object or somewhere else in the image. So it's an estimation of the noise standard deviation. So then that's a measure of contrast to noise ratio, not simultaneous contrast. When you compare images, you could take a few different measures. Mean squared error, FMN minus GMN square, averaged over the entire image. Mean squared. It's not an error, it's a difference. Normalize that by dividing by the energy of the original, F. So the same thing, divided by that, the Mn cancels out. Normalized error, you take the magnitude instead of square. Laplacian says, well, the actual values in the image could be shifted. You're comparing one image with another. Maybe it's the same scene, but I took two pictures with different light levels. The mean squared error will be very large because the intensity values are very different, but the scene is the same. So Laplacian says, don't compare the images, but take their Laplacians. Remove the intensity out and take the relevant edge information, which is important in understanding the scene. So FL is the Laplacian of F, GL is Laplacian of G, normalize with that. That's called the Laplacian mean squared error, which will account for variations in brightness or intensity or exposure. And then there is a measure known as perceptual MSE. In image processing and analysis of imaging systems, some of these errors are mathematical concepts or statistical concepts. But what matters in perception is how our human visual system perceives the details, or how the radiologist or the user perceives. So you have to bring in the characteristics of the human visual system, which acts like a filter. It's a high-pass filter. It's a band-pass filter. Not exactly high-pass. There is a high-pass component in a band-pass filter. Some model it as Gabor filters. So you use that filter instead of the Laplacian, and then compare the images. So PMSE is defined in a manner similar to the Laplacian MSE, but images replaced with a log of the image convolved with a PSF representing the visual system of either the user or the general population. Now these are comparing images before and after, assuming you have the original and then something else that was somehow modified. But you don't always have that. You just have perhaps what you acquired from an imaging system. You don't know what the original is or was. There's no such original thing. You just have the distorted image or the acquired image. Then you need other types of measures. All of these measures need a reference. You need reference-free measures of whatever it is, contrast, high frequency, and so on. So there are some such measures. So I'll now go through one of the applications we worked on based on what is called acutance. Acutance is an interesting concept related to sharpness, edge sharpness, similar to the edge spread function we saw earlier. One of the definitions is the derivative of that edge spread function squared, a to b, where the edge is between a and b, and divided by fb minus fa, the value of that, so you normalize it. So this is acutance. Ideal edge, the blurred edge, more the blurring, the lower the derivative. And integrate between the limits of the blurred edge and normalize by these values, fb minus fa. So that has been called acutance. It is based on the image domain using an edge function, edge image. So many experiments were conducted in order to compare films in the olden days, in the 60s. There were many types of films for X-ray imaging, for mammography, and so on. You want to compare them. How do you do that? Create an edge object, take a picture, take the edge spread function, which is that, and get the acutance value. It was also done with photographic films. and prints were made, or some display was made of the blurred edge images. They were given to a number of observers. They were asked to rank the blurriness or sharpness, and then this was correlated with sharpness as judged by human observers, and it was shown to have good correlation. So it relates well to how human observers will compare or analyze sharpness and rank across multiple images. So they use this to analyze and rank the quality of films for photography and other types of applications. And then there are a number of other measures also called acutance. They use the same name. I wrote a review on this many years ago.
The earlier process, the reverse also can be used like to test the eyesight or something like that.
Could be. Like what you perceive, but you have to explain what you're perceiving, right? So this is to correlate a mathematically derived and computed measure with what a number of human observers have seen. It is assumed they're all standard observers, but some may have some deficiency or some difficulty in observing details. That's why you take a number of observers and average. So you may rank it as 1, 2, 3, 4, 5, and she may rank it as 1, 3, 5, 6. The ranking will be different, so you average. We noted that the area under the MTF curve is important. So the MTF has been used, and the MTF of an entire chain of systems along your imaging process needs to be taken into account. First, you have your X-ray system, and you take a picture on a film, but before the film there is a screen, and there could be a grid, and then you take that and perhaps you digitize it, and then you display it on a monitor, and then you are sitting and watching, so your system is the final one. So there are multiple systems in this chain of image acquisition and display and analysis. So H1 UV, H2 UV, when you have a number of linear systems in series or cascade, the net or total MTF is a product of all the individual MTFs. The image final output is the convolution of the input image with the convolution of all of these point spread functions, because it's going in cascade. So you take that product and take the area under that curve. There are different ways of normalization. The basic idea is a system with large gain at high frequencies will give you a sharp output image. That means large area under the normalized MTF. But MTF area-based measures represent the combined effect of all the systems between the image source and the viewer. It doesn't depend upon the image. So it depends on the system and the viewer and has nothing to do with the actual image, which may be good or bad depending on what you want to do. So if you use radial frequency, nu is square root of u square plus v square, then a measure of acutance was defined as hs nu minus he nu integrated 0 to nu max in the frequency domain. So hs is the MTF of the complete system. He is the threshold of the eye, MTF threshold. Nu is the radial frequency of at the eye of the observer. So that depends on the distance between the display and that's the angle subtended. Nu max is given by this condition. Hs nu max must be equal to He nu max. So that was another measure. And then somebody else said, well, don't take a difference, take a ratio. I can go 0 to infinity or 0 to some limit in frequency. And another researcher said, well, we need to normalize and get numbers like in marking exams up to 100. So scaling factors. So they said 100 plus 66 log 10 product of the two MTFs divided by the integral of the I MTF ratio. This is just a normalization factor, so 100 is excellent. And 70 is just passable. Not 35%, not 50%, but 70%. That used to be first class with distinction for me. Nowadays, all of you get 99.9, I suppose. For us, 70% was top. The exams were tough. That's what we put the blame on. That's the excuse. But really, 70% was first class with distinction. Is that so now? What is it, 90?
Distinction only like same.
70. But you're all way above that. Good. Oh, yes. You see, he says yes, and you were nodding your head. Okay. There was another one who said, take the ratio and square root, d nu divided by nu, inverse weighting with frequency. You don't have to remember all this, but just know that there are different ways of comparing the MTFs. Difference is one, ratio is another. And integrate and some normalization. Barton has a nice book on just acutance, a whole book. It's interesting. We wanted to extend this definition of acutance to a specific image, to a specific object in an image, in particular tumors. Benign masses in X-ray images have a sharp boundary. The inside is dense, outside is less dense, and the boundary is sharp. So if you take a derivative across the boundary, the value of the derivative is high. But we have to take the derivative in a different way, as I will show you. Whereas malignant tumors are blurry. Their edges are blurry, and because the cancer is expanding and infiltrating surrounding tissues, there is no sharp edge in the case of malignant tumors. Now, such things we gain by interacting with radiologists and chatting with them, and they would come to our labs, I would go there. To go away from this topic a little bit, it is very important in this kind of work to collaborate. There is only so much we can do sitting in our own labs in front of our computers. These ideas that I'm talking about were given to us by radiologists. They know what kind of images there are and what are the differences between type A, type B, benign, malignant, this, that. And in my opinion, in my work, I felt our task is to encode that, to quantify it, to capture that and write algorithms, develop algorithms to measure that in a quantitative way so we can do objective analysis. The radiologists will say this is blurrier, this is sharper, but put a number on it for us. I call that collaborative or collective intelligence. As I said, I don't like the term artificial intelligence. Everything is AI nowadays. This is not AI, this is CI, I'll call it. Collaborative, the collaboration is very important. I wouldn't have been able to do this myself. The radiologist, I would assume, would not do that by himself or herself, but together we do something that is useful. That collaboration is important, and credit should be given where it is due. To call this artificial is, I think, demeaning and taking away the contribution of others, not only radiologists, but medical scientists and others. But anyway, the world is going in some way with Trump and Musk and others. So we said we want to get a measure of the sharpness of the edge of objects such as tumors. So instead of using the traditional difference, as we call it, derivative or first difference, Fn minus 1 in a single row, we said you jump across the edge. What is inside the object and what is outside, at multiple scales or multiple distances. So if this is the boundary, we said draw a normal at every pixel. Normal is perpendicular to the tangent at that point, the normal. This is the edge point, we don't use it. 1 pixel distance inside and outside, take that pair. What is the difference? If the inside is brighter than the outside, that's a large value. And then do that for different distances, maybe 2, 3 distances. But we're not taking differences like this and this and this and that. And do that at every pixel all the way around. So there is averaging for each normal, and then there is averaging across the whole object. So that is Fn minus Bn, foreground minus background. And the distance between them for n is 2n, 2 pixels, one inside, one outside. And n going 1 to n some number, that is one gradient at one normal, and then average that over the entire image by averaging over all of these normals. So if there are capital K of those normals, then that is the root mean square value of that. So we call this acutance, not knowing all the history. When we sent it for publication, I got very critical reviews. Oh, you forgot all of this. There's so much history behind acutance. So then we went back and reviewed all the literature and put this in the context of all of that, and then it was published. So acutance we showed by conducting subjective analysis, showing images to a number of observers, and computing the acutance value and correlating with subjectively ranked sharpness. So we took a test image, blurred it once, twice, 3 times, 4 times, blurrier and blurrier, added noise, and then we showed that it is reduced by blurring, increased by sharpening, not affected significantly by noise because of averaging of the derivatives, and correlates well with sharpness as judged by human observers. We also applied this to analyze breast tumors in mammograms. I'll show that later on. Okay, that finishes chapter 2. I skipped some parts that are not very important. You could read them later on. We will switch to chapter 3 now on filtering, and that includes, again, some background on linear shift invariant systems, convolution, some numerical examples. I'll go through them quickly because many of you already know that. But are there any questions right now before we switch to the next chapter?
Rather a remark, you said artificial intelligence. I started feeling that is true.
It is.
Not giving credit to the radiologist or medical doctor, but in artificial intelligence neural networks, we need the knowledge of that. Finally, we don't even credit to the artificial intelligence. It takes over.
Yeah. Excuse me. What has been shown is that AI-driven, deep learning-driven systems have catastrophic failure. They're trained with a certain data set, let's say in Europe, with European images of patients or whatever, and then come to India and put Indian images, they collapse. Because they're trained only with that. Whereas if you extract measures that you have designed specifically, what one of my colleagues has called handcrafted features, like you do a matka or something with a wheel, and it is specifically designed. But it incorporates the knowledge of the radiologist and our knowledge as electrical and computer engineers, and it is expected that it will work across multiple regions, multiple types of images. The same thing applies to tumors anywhere in the brain or wherever it is. The same thing happens. Benign versus malignant. I've heard from other researchers when I presented this, they say, oh, that's breast imaging, yeah, but it's similar in the brain. And true, that's a basic biological variation between benign and malignant. Whereas if you simply stuff 1 million images, it catches something. I haven't done research in this area, so it's uninformed and biased opinion. But I have read reports where it says some of these systems do fail in a disastrous manner when new samples are presented because they haven't been trained with such. But when we did our research, it was hard to get 10 samples. Now in 30, 40 years, things have changed and there are millions of images available to you. There were no public databases at that time. We had to go and get the films and digitize them, scan them in our lab. My students spent a lot of time doing that kind of work. Now you just go somewhere and download a million images. So things have improved and changed, yes, but I think it is important to recognize where this information comes from and give due credit there. There are some computer scientists, I won't name any, who have claimed, well, computers will replace radiologists. There won't be radiologists anymore. And it is true, they have said that. Very influential computer scientists have said that, AI specialists. And my colleagues in Brazil who are radiologists have told me that led to a drop in residents coming to radiology. So that is irresponsible to say that and cause such a shift in the preference of students. The students should know better, but they will trust such information coming from somebody who is highly placed. And so, radiology won't be there anymore, so I won't go there. And that's not correct. What are artifacts? There could be noise, there could be some kind of a pattern that you're not interested in. So basically, any image pattern or signal other than what is of interest could be termed as interference, artifact, or noise. Usually we assume when you say noise that it's random with zero mean and uniform distribution, but not necessarily so always. Anything that you don't want, like that, somebody scribbled there, that's noise. So that's a general opinion, or not opinion, view of noise. But there are different types of artifacts. So when you design filters, you need to know what kind of artifact you have and how to remove that. Random noise is present always. Interference from a random process such as thermal noise in electronic devices, CCDs, and counting of photons, X-ray photons or gamma ray photons. The emission process is random, the counting process is random. So everything is random. And you characterize random processes by their PDFs. So let's call that noise is represented as eta, p eta of eta. So this notation, the subscript is important because that is what the original process is. The argument could change when you integrate and apply various processing steps. So the noise process is simply a bunch of values being thrown out by something, some disturbance in the air, random variations in temperature. You have a number of CCD elements and each one has some dark current and some noise. Where are you putting those values is the question. If you put them in a time function, in a time series, it's eta of t. If you put them as a function of space, eta x, eta xy, xyz. So those individual values are coming from some random process. If you arrange them in a pictorial format, you have a picture. Otherwise, it could be a time function. So it could also be eta xyz time, 4D. 3D function as a 3D data as a function of time. So regardless of how those values are arranged in your signal or image, the statistics are defined based on the PDF. So mu, the expectation value, is integral of eta p eta. E is the expectation operator. That, whatever that is, multiply with the PDF and integrate. Second moment, mean squared value, eta square. Eta square times the PDF. Variance, eta minus mu square, PDF, integrate. So variance is the second central moment. Square root of variance is the standard deviation. So eta square is expectation of eta square minus mu square. If the mean is 0, then these two values are equal. Variance is equal to mean squared value. So just an example, Gaussian distributed values put as a time series. Mean 0 and sigma squared is 0.01. Mean squared value is 0.01, RMS is 0.1. And if you put that as a picture, you get that. As a time series, you get this from the same process. The PDF is that which is approximately Gaussian. So when you have an image, biomedical or otherwise, FXY, you may say, well, there are so many of these images in my collection. So many patients come, there are so many pictures taken. So even those are random. They're not exactly random, they have structure, but there are variations. So in general, you can say everything is random and treat them as random observations of a random process. Each one is a realization or observation or a sample of that process. So this allows statistical characterization. So a collection of images of the same organ, system, or type, and population limitations, age limitations. You don't want to mix pediatric cases with adult cases. You don't want to mix images of female subjects with male subjects, or Indian with European, and so on. So you have to have separate databases because of variations in the body or in ethnicity and place of living. So collection of images of the same organ, same type, same imaging modality, same settings, everything being the same, then you can characterize them statistically. Take the average PDF, average histogram, then it's a PDF. And then you can characterize them in terms of their statistics. If you mix various types of images, CT with MR and brain and liver, that doesn't help. So statistical averages representing populations of images of a certain type are useful in designing filters. Which filter is most suitable for that kind of image? Data compression techniques, pattern classification procedures that are optimal for that specific type of images. But one should recognize that in medical imaging, we are not interested in the average. Not we, but the radiologist or the physician, the cardiologist is not interested in the average, but what is the difference between the average and this patient? That is where diagnosis comes in. So deviation from the normal is what is important. But that's what they do. So when an image is observed in the presence of random noise, we assume this model, additive noise. And each one has its own PDF, PF, P-eta, PG. We assume they are statistically independent processes so that the joint PDF is the product of the individual PDFs. The expectation of G in this case is additive. The means are additive. Mu G is mu F plus mu eta. That happens due to linearity. But with statistical independence, you also get this relationship. The variance of G is the variance of F plus variance of eta. The powers get added. Now, there are different ways of taking averages. One is with the PDF, if you know the PDF. But if you don't have the PDF or don't know, or you want to do something else, there is the possibility of ensemble averages. An ensemble is a collection of images of a certain type, or the same image being acquired repeatedly for the given situation. So you have a number of sample observations, F1, F2, F3, and so on, of the same. I take a picture here, I stand here and take click, 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 and I take many pictures. What is the variation? Assume nobody is moving. The variation could be some noise here or CCD, noise in my detectors. So there'll be some variation. Then I can do ensemble averaging of the images. The whole string of images can be averaged, assuming there is no motion, no registration issue. So you have a stack of images, and the ensemble average is taken using pixels that are registered for each pixel through the ensemble. You can also take spatial averages in one image. If you only have one image, you average like that. But if in an ensemble average, you go through multiple images to get mu f x1, y1 for x1, y1 one location, and do it for each pixel. So mu f x1, y1 is 1 over m, k going 1 to m, f k x1, y1. There are capital M number of observations. For each pixel, you average across those. And divide by m for normalization. Limit m tends to infinity means you need to have a large number of images. Nobody will acquire an infinite number of images, but a large number, 10, 20, whatever. That helps in reducing noise. The autocorrelation function is defined as phi f x1, x1 plus alpha, y1, y1 plus beta, some shift of the given image, fx1, y1, and the same image with x1 plus alpha, y1 plus beta, shift of alpha, beta. Multiply them, take the expectation. I earlier defined a correlation function where you just took the dot product between the original and the shifted version. Now this is in terms of statistics, expectation. That means you have to multiply that with the PDF and integrate. But you estimate in this manner. You say, okay, you have capital M of the images. I don't have a PDF, but I have a number of observations. So over a number of images, Fk, k going 1 to m, and Fk with the shift. And divide by m, large M. If the process is stationary, the autocorrelation function depends only upon the shift parameters, phi f, alpha, beta. So this x1, y1 will go away. That requires stationarity. Then autocorrelation is a function of the shift only, and the Fourier transform of that is not dependent upon the spatial position x1, y1.
So the sample estimate is, we assume that the sample estimate is works in real time, right? That's what we assume. Sample estimate is in real-time applications. We assume that the sample estimators work better. That's what we.
You mean this? Yeah. Than compared to what?
Like other estimators, other than sample estimate.
Yeah, if you, PDFs are usually based on some models. This is based on the actual samples you have measured or observed. So when mu of x1, y1 is computed for every location of the image, you get an average image. That is, average of a number of images of the scene I acquire. I get an average image. And if there is no motion or movement of anything, it's a cleaner image because noise averages out. The value of the noise is reduced. So we call that F bar, and you could call that a prototype or simply a filtered image. But it is filtering through a population of images. So those are ensemble averages, averaging a collection of images. Before that, we said we can take statistical averages using the PDF. If you don't have the PDF, go for ensemble averages. And there are situations where you don't have an ensemble. You only have one image. Take it or leave it. And then you can only work with that one image. Then you go for spatial averages or temporal averages if it is a time domain signal. So when you have a sample observation of a process as a function of time, you may compute time averages or temporal statistics. Mu of k, fkt, now it's a function of t. And that is an observation k. And you make multiple observations, but the integration is on time. The averaging is on time, and 1 over t is normalization over a large time window. Autocorrelation function is this, fkt plus tau. Tau is a shift. Integrate over a window and make that window as large as feasible. So given an observation, fkxy, we may compute spatial averages or spatial statistics. Instead of time, now space. So mu fk is integral of fkxy dx dy, now on space, averaged by the area of the image A. But this is one value for the whole image. The average, mean value, mean intensity, mean density, whatever, one value. It's not very useful. It's not a picture anymore. The autocorrelation function is given by alpha, beta, k, where you have kth observation. There are multiple observations of the kth image fkxy and fk with the shift. Dx dy integrate over space. You may normalize this with phi f00, which is the energy of the image. If you want that to be normalized, then it will be maximum of 1. The sample index K is irrelevant if you only have one image, one observation. Then you can only do spatial averaging on that image. So when you have a TV image or an image as a function of time, and it need not be like multiple frames over seconds, but it could be images of the same patient over a few months or some time. Then you have a series of images, and there is a time factor there as to when the image was taken. So then you have fxyt or fxyzt if they are CT or 3D images. Then you can do all these operations in all the space coordinates and the time coordinate. If you compute the statistics using one frame, it is called intra-frame. If you compute statistics between frames, it is called interframe. So interframe and intra-frame over a 3D data set. So this could be multiple frames of a TV signal or multiple images of a patient over time. And if you take averages over one image, you call that spatial or intra-frame. If you go across the collection, previously we called the same thing as ensemble averages. Now here the ensemble has a time index, so you call it temporal or interframe statistics. So there are many possibilities of getting statistical measures from medical images in 1D, 2D, 3D, 4D, time, space, with PDFs, ensemble, and so on. So one needs to recognize which method is suitable or which has been used in gathering this information.
The sequence is not the relation of the sequence that you have some of the frames like this. These are not the relation of any of the.
What's that?
They are not the relation of some random.
No. Here, they are not. Here they are not random. No, this is my image taken today, tomorrow, and so on, or my image taken as a video. So it is an image that is of a certain type and of a particular patient if it is a patient's image over time, or video. There is no randomness here except the noise. There could be noise there. Yeah, even the other case, the ensemble, they're not random. The ensemble is a picture of a scene. My picture taken many times because your CCD camera or whatever camera you're using has noise. If you're using a thermal camera and night vision, then you don't have much light. So there is a lot of noise. So if you take my picture and it's very noisy, grainy, you take multiple shots asking me to be steady, and then average, you get a better image. So the randomness is there in the noise, but not in the picture. Is that what you said? Yeah, okay. So the mean is not important, it's the average brightness, and you don't throw it out, you need it for display. In signal processing, 1D signal processing, often we remove the mean. In speech processing, there is no mean is zero. Mean average value doesn't mean anything in speech. There is no variation, right? But ECG, there could be an average value. Heart sounds, no. EMG, no. Where is mean important? Not many places. But images, the mean is important because that's the average brightness. The autocorrelation function is important in the characterization of random processes, given that the Fourier transform of the autocorrelation is the power spectral density. You get the power spectral density, which is useful in analyzing the frequency content and designing appropriate filters for that class of images. So these statistical functions are useful in the analysis of the behavior of random processes, in modeling random processes and also populations of images, spectrum analysis, filter design, data compression, data communication systems, and so on. You need to know these statistics in order to design optimal filters and procedures. If you just want to do something ad hoc, fine. But if you want to do something optimal, then the optimization procedure will require some of these statistics, especially the autocorrelation and MTF. A few examples of PDFs. By looking at the distribution, you should be able to judge what kind of a function it is. Gaussian is this. You have mean and the variance, exponential with the normalization factor. It is completely specified by the mean and variance, only 2 parameters. Looks like that. Everybody knows Gaussians. Different, same mean but different variance and different mean. When you have 2 jointly normal random processes, then the normal bivariate normal PDF is given by this Gaussian with this correlation factor. This is one Gaussian, this is another Gaussian, and the normalization factor includes the variances of the Gaussians and this 1 minus gamma square. The gamma comes here as a weighting factor and here. And gamma is the correlation coefficient given by expectation of x minus mu, y minus mu I, divided by sigma x, sigma I. And if they are uncorrelated, gamma is equal to 0, and then that goes away, that goes away, that goes away. You get a product of 2 Gaussians. So the bivariate normal PDF reduces to a product of 2 univariate Gaussians, and they are statistically independent then. There is a central limit theorem that is important related to the occurrence of Gaussian PDFs and the assumption of Gaussian PDFs. It is common to assume when you don't have adequate information, well, we'll take it to be Gaussian. Why is it important? Because the PDF of a random process, that is the sum of several statistically independent random processes, is equal to the convolution of all the individual PDFs. This is from, if you have seen the book by Papoulis, Random Variables and Stochastic Processes. That's where we studied. When a large number of functions are cascaded and convolved, then all these convolutions will lead to something that is smooth like a Gaussian. If you take a rectangle function and convolve with another rectangle function, you get a triangle. Convolve again with another rectangle, you get a smooth triangle. Convolve with the same rectangle function convolved 3-4 times will lead to a smooth result that looks like a Gaussian. All of these are positive valued functions, so there is only smoothing, no differentiation anywhere. So regardless of the forms of the individual functions, they tend towards a Gaussian. So that's why it is assumed commonly that the noise has that shape. But sometimes we do have uniform functions. Uniform, all equal, all probabilities are equal, all values occur with equal probability. The mean is a plus b over 2, where a and b are the limits of the rectangle, and sigma square is b minus a square over 12, just a rectangle. The Poisson noise is important in imaging, medical imaging, especially in photon counting, single photon emission computed tomography, gamma camera imaging. The counting of discrete random events, such as the number of photons emitted by a source or detected. There could be a number of photons coming, but your detector will not catch all of them. They will catch some. And there is a randomness in the emission process and the detection process. And the discrete nature of photons and the statistical randomness in their emission and detection contribute to uncertainty. You can call them quantum noise, photon noise, Mortal, Poisson noise, and short noise, depending upon the source and the type of system you're using. One of the formulations of the Poisson PDF, there are at least 2. I'll show one here. Pk is exponential minus mu, mu to the power of k over k factorial. Mu is the mean, average number of photons counted in the specified interval of time over many trials. Pk is the probability of occurrence of k, and the variance of the Poisson process is equal to its mean. But the Poisson PDF tends towards a Gaussian for a large mean, but it is one-sided. So the Poisson PDF ends here, it's not for negative values. But as you increase the mean, it looks like a Gaussian, becomes close to a Gaussian. This is for mu equal to 4, that is mu equal to 20. The Laplacian is encountered when you take derivatives and differences. And the Laplacian distribution is defined in terms of a mean and standard deviation. And this exponential function, it's an exponentially decaying two-sided function. You encounter them also in linear prediction and prediction error. Looks like that. Laplacian distribution, 0 is in the middle. Sigma square equal to 1 and 4. The Rayleigh distribution is encountered in some types of imaging, especially with ultrasound and a few other types of imaging. Let's not worry about the form. I'll show you the graph of that. It looks like that, which is not symmetric. And it is one-sided. So we'll stop here and take a break. If I'm going too fast, let me know. These are just some basic things I'm reviewing quickly. When there are more important things, I'll go a little slower. But if something is not clear, please stop and ask questions.